And good morning, everyone. My name is Tang Jahek from the course SIF2003 Electromagnetism 2. And welcome to my presentation on waveguides and transmission lines in electromagnetism. So first, let's start with the waveguides. And what is a waveguide? Might be a question. So a waveguide is a structure that guides the electromagnetic wave from one point to another. And a waveguide are typically hollow metallic tubes, or they can also be dielectric with cross-sectional shapes that can be rectangular, circular, or more complex. The structure confines the electromagnetic wave within its walls, and yeah, there are a few types of waveguides that each of them designed for specific applications. Here are a few examples. And firstly, we have circular waveguides that is used for high power transmission. Next, we have rectangular waveguides. They are the most common type used in various microwave applications. And we have twist waveguides used to change the polarization of waves. And finally, there is 90-degree elbow waveguides that used to alter the direction of wave propagation. And next, about the theoretical part of waveguides. So we know the waveguide behavior is governed by Maxwell's equations in matter. So these equations describe how the electric and magnetic fields propagate through the waveguide. By solving these equations, we will know the general solution for electromagnetic wave propagation. And yeah, so I need to mention here the gamma square from the wave equation is defined by the waveguide parameters, which are mu, sigma, and epsilon. Okay, so let's look at an example of a rectangular waveguide. This type of waveguide consists of a rectangular metallic tube which confines the electromagnetic wave and support the modes of propagation like TE and TM stands for transverse electric and transverse magnetic modes. So in this diagram, the propagation of wave is assumed along the z direction. So we can see in TM and TEM modes, the electric field or the magnetic field will be zero along z direction. Yeah. So in a waveguide, we know not all the frequencies propagate equally. Instead, we have cutoff frequency below which the electromagnetic wave do not propagate. And we have evanescent range of frequency. The electromagnetic wave will decay exponentially within the range of evanescent frequency and do not carry power. And lastly, we have propagation. The only those electromagnetic waves above the cutoff frequency can propagate efficiently. And then next, we know the characteristic of waveguides in general. And firstly, it's about the modes of propagation. There are different patterns of field distribution throughout the propagation in waveguides. And secondly, the cutoff frequency is very important. It is the minimum frequency at which a mode can propagate. And finally, the dispersion. That is the variation of phase velocity with frequency, which affects the signal integrity. Yeah. After propagation over a long distance. Yep. And next, about the applications of using waveguides in various fields. So first, in telecommunication system, such as fiber optics and microwave transmission, will use the waveguide. And next, in scientific research, such as particle accelerator and spectroscopy and quantum computing as well. Thirdly, in radar systems, the waveguide is used in air traffic control and weather monitoring, and also in medical instrument, we use it in MRI machines and endoscopy. Next, let's talk about in detail about the optical fibers. Optical fiber act as a waveguide for light, transmitting data over a long distance with high bandwidth and lower loss. They are fundamental to modern internet infrastructure. And how about the advantages of using waveguides? Firstly, we know the waveguide provide a high bandwidth. They can carry a vast amount of data, especially for single mode fibers, which are ideal for long distance and high speed communications. And next, they provide a low attenuation. There has a minimal signal loss over the long distance, including undersea cables. And lastly, is about the security. It is more secure than electrical transmission because tapping an optical fiber without detection is challenging, or in other words, it is impossible. Okay, so then next about scientific research that is using waveguides, especially in particle accelerator. So we focus on the advantages of using waveguides. Firstly, the waveguide can provide efficient power transmission, which enables the efficient transmission of high power RF, stands for radio frequency energy, from klystrons to cavities, which can minimize the energy loss and ensuring the effective of particle acceleration. And secondly is to allow us use a precise control. Waveguides allow us for precise control of the radio frequency fields within the cavities. Yep, that is all for waveguides. Let's move on to transmission lines. This transmission line. Transmission line is a specialized structure designed to conduct electromagnetic wave as electrical signals between 2 points that minimize the loss and controlling the impedance. Okay, so there are also a few types of transmission lines, and I show you in this diagram. Okay, so for example, the coaxial cables that are used for high frequency signals. Next is the twisted pairs that is commonly used in telephony and networking systems. And lastly is about the microstrip lines that is used in printed circuit boards for RF signals in electronics. And then we know the theoretical part. Yeah, as we know, the behavior of transmission lines is described by transmission line equations, which plays the similar role as Maxwell equations as previously. And the transmission line equations relate the voltage and current along the line. And these equations are important for designing efficient transmission system. Okay, and the transmission lines can be characterized as lossless lines and distortionless line. Lossless line is an ideal line with no attenuation at all, and about the distortionless line is a real line which is designed to minimize the distortion by balancing inductance and capacitance per unit length. So next, about the characteristic of waveguide, about transmission line. So we have the attenuation and impedance. So for attenuation, it is a loss of signal strength as the wave travels through the transmission line. And about the impedance, that is actually resistance to signal flow, which must be matched to minimize the reflection. And about the application of transmission line. Yeah, in telecommunication system, we use transmission line also in telephone lines, internet cables, for example, the Ethernet. And secondly, in power distribution, we use it in electrical power grids to transmit power generated over a long distance. And besides that, we use it in electronic device. The transmission line can be found in printed circuit board for signal routing. And lastly, in broadcasting, the signal transmission in radio and TV broadcasting system will use the transmission line to propagate. And as a conclusion, I made a comparison between the waveguide and transmission line in terms of their structure, frequency, and lossless, and also the applications in the table. So yeah, the most important part is about the frequency range and lossless of these two structure. So we know the waveguide has higher frequencies to operate, and transmission line has lower frequency range to operate. And the waveguide has a lower loss at higher frequency compared to the transmission line. Yeah, so that is all for my presentation today. And These technologies are fundamental in modern electromagnetism today, and they have a wide range of applications in various fields. So, thank you for your attention on this presentation. I am Tang Jahid. Yeah, thank you so much.